Okay, welcome back. When we left off last time, I told you that we pick up here next time. What is an electrical circuit? Well, a circuit is a closed path. So it's a closed path for electricity to flow around. There's no openings or breaks. List the parts of a circuit and draw a picture for the relevant components. Well, here are the components: wires, resistors, light bulbs, cells, which are the power sources, and batteries, and switches. So here's a series circuit, and we said there's only one path around. And I made it like an oval on purpose because there's just one path around. And we're going to add in the pieces. So we're going to add in a battery, but there's still one path around. We're going to add in a switch. Right now it's open, so the electricity wouldn't flow. We're going to put in a bulb. We're going to put in a second bulb. We're going to put in a third bulb. We're going to put in a fourth bulb. We're going to put in a fifth bulb. Okay, now right now the switch is open. We're going to close the switch. The electricity flows around now to the bulbs, so they'd all be on. But as it goes through, bulb one's going to use some, then bulb two, bulb three, bulb four, and bulb five is all going to be using electricity because each one gets what's left from the last one. So they would get dimmer as they go around this circuit. If any one of them goes out, like bulb four, I just removed it. The path is now open and the electricity can't make it around, so they would all go out. So this is like those holiday lights where people say, you know, you got to check every bulb. So if one of them goes out, then they all go out. Now, you know, sometimes kids say, well, sometimes they still keep working. They've tried to make these things better by putting in like little dumper wires to go across. So even if the bulb is burned out, there's still a little path for the electricity. But the idea is basically the same. Okay? Any of the bulbs go out, okay, it can't make it all the way around. If we replace the bulb and stick it back in, then there's a complete path for the electricity. Okay. Draw a parallel circuit. Okay, the wires in a parallel circuit are parallel. They're not like this loop in the series circuit where I started off with the oval. There's two parallel wires. You have to hook them to a battery or a power source. Okay. We're going to put in a switch, which right now is open. Okay. Then the things go in between the two pipelines. So the first bulb is here. The second bulb is here. The third bulb, the fourth bulb, and the fifth bulb. Okay. And now the switch was open, so none of these bulbs would be on. Now the switch is closed, so they would all come on. But when the pressure goes down here, okay, this is like the main pipe carrying the water. So when it branches off to these different things, they all get the same amount of pressure. Okay, so right now it would be on. If one of them goes out, like I just removed that bulb, okay, there's still pathways around. So one of the things can go off and they don't all go off. So this is why we wire our houses that way. Okay, if something else goes off, let me put them back. So, you know, it's on right now. If this first one, like you turn off the lights in the kitchen, so it's no longer part of the circuit. Everything else in the house still stays on. Or if you turn off the stove, the other things like the TV and the toaster and another light bulb all stay on. Okay. That one goes out. These can still stay on because there's pathways around. So the advantage of a parallel circuit is that one or more parts of it can be turned off and the other parts can still stay on. Okay. Why do we use electricity and what can it be turned into? We use electricity because it can be stored in batteries, it can be transported through wires where there's no pollution, and it can be changed into mechanical energy, thermal energy, chemical energy, electromagnetic and radiant energy and sound, which means it's very flexible. We can turn it into almost all the other things that people want to do. Now, electricity and magnetism are strongly linked. Okay, remember we said there was around a place where there was an electric charge, there was a strong magnetic field. And so whenever there's a current carrying wire or something that could potentially carry current and it gets in a magnetic field, the magnetic field pulls and pushes on the electrons, and that causes the electrons to flow. So magnets can make electricity. And we're going to take a look at the relationship between the two. Magnetism itself is defined as the properties and interactions of magnets. A magnet is a material that produces a magnetic field and interacts with other magnets. And just like an electric field, a magnetic field is that visible bubble that surrounds a magnet, and it exerts a magnetic force. So just like we saw that man make the electric field around the wire, there's a magnetic field around a magnet. And it's the push or pull created by the magnetic field. Okay, and we know that magnets can operate on things even at a distance. And just like electric fields, magnetic fields, and just like gravity, all of them depend on the distance you are from the source. So with gravity, the closer you are to the source of the gravity, like the Earth, the stronger the gravitational field. The closer you are to the electric wire in a magnetic field, in an electric field, the stronger the electric field. And just like a magnet, the closer you are to the poles, okay, the stronger the magnetic field. So like you know this, if you're going to stick a refrigerator magnet on a refrigerator, you have to get it close to the refrigerator in order for the magnetism to work. And so here's another picture of these magnetic fields, and we see it flowing from the positive end to the negative end. Okay, so in this case, it's flowing from the North Pole to the South Pole of this magnet. And here's why these two magnets repel when they have like poles, because it shows the field lines that are pushing out from this one's North Pole to this one's South Pole, and from this one's North Pole. So when they bump into each other, they're pushing against each other. So this is why you can't push two like poles together. When you bring magnets together so that they have opposite ends, and they attract. So just like it's going from the north to the south here, it's going from the north to the south here. Magnetic poles are the regions where the magnetic force exerted is the strongest. So here at the ends of the magnets, where we have the north end and the south end, these are the poles. And this is where the magnetic field is the strongest. This is where they're going to attract or repel the most. So in between, in the middle of the magnet, there's not much of a magnetic flow. So if you've ever played with magnets, like we get them in the middle, they'll flip around so that the poles are matching each other. So it's that area where the magnetic force is the strongest. All magnets have a north pole, which is positive, and a south pole, which is negative. So again, here it shows the charges are flowing from the positive to the negative. Okay, so we have these magnets down here, and it shows that when we have the north, which is positive, and the south, which is negative, we have the like poles, they repel. And unlike or opposite poles, attract. So looking down here at these magnets, these like poles to the south are both going to repel, and these opposite poles, south to the north, are going to attract. And these ends of the magnets, where the north and the south end is, those are the poles. And this is why a compass needle always points north, because it's just one of these bar magnets that's free to spin. And the Earth is a ginormous magnet. So it lines up so that the opposite ends of the compass are pointing to the poles of the Earth. That's why the compass needle always points north. And it's a little bit different than north on a map, okay, because the magnetic pole of the Earth is a little off-shifted. So if you do this, there's some lines of reclamation that you have to deal with. Okay. Now, why do things become magnetic? They become magnetic because of the individual atoms. each individual atom in a magnetic material like iron, cobalt, or nickel has its own little poles. When they all get lined up and they're all together in the same way, they add together and make what's called a magnetic domain. So magnetic domain is a group of atoms aligned with like magnetic poles. And the magnetic field, so these are aligned down here. So you can see each one of these little bar magnets inside this big magnet represents a little individual atoms. So it's showing all the atoms are pointed in the same way. So all the north poles are pointing to the one end and all the south poles are pointing to the other end, and they're all lined up. This would be a strong bar magnet. In this one, where they're all jumbled up, this would be non-magnetic. So this would be like a piece of iron where you would put it in a strong magnetic field and force the irons in the atoms in the iron to turn around and get lined up, and it would be a magnet. This would be just a nail, okay? A piece of metal where the atoms are jumbled. And this is why they tell you not to drop bar magnets, because you take this bar magnet where they're all lined up, and if you keep dropping it, they'll jumble them up like this, and it won't be a magnet anymore. Okay. So magnetic fields are created by each atom, which exerts a force on a nearby atom. In a magnet, the like poles all point in the same direction, like this example down here. These are called permanent magnets, and they can be placed by piecing a piece of iron in a strong magnetic field. If you leave it there long enough, the atoms in that piece of metal, like iron, will turn around, and eventually over time they'll get lined up, and they'll stay lined up. They get comfortable in their new position, and then they stay that way. These materials are called ferromagnetic. So that's why iron on the periodic table is Fe, because remember it was ferrum. So it's things that are ferro, which is the Latin for iron, magnetic. So they're those groups of materials that have magnetic properties. So it's things like iron, cobalt, and nickel. Okay. Non-metallic, not all metal is metallic. So for example, aluminum, okay, it does not have its atoms lined up. Ferromagnetic, neodymium can be added to increase the magnetic properties of the ferromagnetic metal. So you sometimes see magnets that say they're neodymium. If you add this, it increases the magnetism of iron. If you take one of these things that has all lined up poles and you break this magnet in half, you end up with two magnets, okay? Because if you split it in the middle, you still have the atoms on this half lined up and the atoms on that half lined up. And if you split it in half again, okay, you would just have four magnets. So one of the questions is what happens if you divide a magnet? Well, you just end up with two smaller magnets, and then you divide it again, you end up with four smaller magnets. We're going to stop here. I want you to answer these questions on your own. And when we come back next time, we'll go over this. I hope you're having a great day, and we'll see you soon.